To determine the appropriate size of the service entrance and the underground feeder, or off, wire gauge for your 3-car detached garage, several factors must be considered. These include the total anticipated electrical load within the garage and the applicable electrical codes. Firstly, let's address the service entrance amperage. To calculate this, we need to estimate the total load. This involves adding up the amperage requirements of all potential electrical devices and appliances that will be used in the garage. This includes lighting, power tools, welders, air compressors, electric vehicle chargers, and any other electrical equipment. It is prudent to overestimate the load to account for future needs and expansion. Secondly, consider general lighting and receptacle circuits. A standard approach is to allocate at least one 20-amp circuit for general purpose receptacles and a separate 15-amp or 20-amp circuit for lighting. Thirdly, account for any specific large power tools or equipment you plan to use. Welders and air compressors, for example, can draw significant amperage and require dedicated circuits. Consult the nameplate on each piece of equipment to determine its amperage requirements. Fourthly, electric vehicle chargers represent a substantial load. Level 2 chargers, which are commonly used for home charging, can draw between 30 amps and 50 amps. Factor this into your total load calculation if you plan to install one. Fifthly, once you have estimated the total load in amps, you can determine the required service entrance amperage. It is generally recommended to add a safety factor of 25% to the total calculated load to account for simultaneous operation of multiple devices and future expansion. For example, if your total calculated load is 60 amps, multiply that by 1.25, resulting in a required service entrance amperage of 75 amps. In this case, you would likely choose a 100 amp service entrance, as it is a common standard size. Sixthly, the National Electrical Code, or NEC, provides guidelines for service entrance sizing. Consult your local electrical inspector or a qualified electrician to ensure compliance with the NEC and any local amendments. Now, let's address the underground feeder or off wire gauge. The appropriate wire gauge depends on the amperage it will carry and the distance of the run. The longer the run, the larger the wire gauge needed to minimize voltage drop. Voltage drop occurs when the voltage at the end of the wire run is lower than the voltage at the source due to the resistance of the wire. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To determine the appropriate wire gauge, we will use the NEC voltage drop calculations and ampacity tables. Ampacity refers to the current carrying capacity of a wire. The NEC provides tables that list the ampacity of different wire gauges based on the wire type and installation method. Firstly, determine the allowable voltage drop. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. For an 85-foot run, a 3% voltage drop is a reasonable target. Secondly, calculate the allowable voltage drop in volts. For a 120-volt circuit, a 3% voltage drop is 3.6 volts, which is calculated by multiplying 120 volts by 0.3. For a 240-volt circuit, a 3% voltage drop is 7.2 volts, which is calculated by multiplying 240 volts by 0.3. Thirdly, use the voltage drop formula to calculate the required wire size. The voltage drop formula is voltage drop equals 2 times K times I times D divided by circular mils, where voltage drop is the allowable voltage drop in volts, K is the constant for the wire material, which is 12.9 ohm circular mils per foot for copper and 21.2 ohm circular mils per foot for aluminum, I is the current in amps, T is the one-way distance in feet, and circular mils is the cross-sectional area of the wire in circular mils. Fourthly, rearrange the voltage drop formula to solve for circular mils. Circular mils equals 2 times K times A times D divided by voltage drop. Fifthly, plug in the values into the formula. For example, let's assume you need to run a 60 amp circuit 85 feet using copper wire with a 3.6 volt drop. Circular mils equals 2 times 12.9 times 60 times 85 divided by 3.6, which equals 36,775 circular mils. Sixthly, consult a wire size chart to determine the corresponding wire gauge for the calculated circular mils. A wire size chart will show the circular mils for different wire gauges. For example, a number 4 American wire gauge, or AUG, copper wire has a circular mil area of 41,740, which is sufficient for this application. A number 6 AWG copper wire has a circular mil area of 26,240, which is insufficient. Seventhly, consider the ampacity of the wire. The wire must be able to safely carry the anticipated current without overheating. Consult the NEC ampacity tables to determine the ampacity of different wire gauges based on the wire type and installation method. For example, number 4 AWG copper wire with a type UF insulation has an ampacity of 70 amps at 75 degrees Celsius. Number 6 AWG copper wire with type UF insulation has an ampacity of 55 amps at 75 degrees Celsius. In this case, a number 4 AWG copper wire is needed as it can carry 70 amps, which is more than the anticipated load of 60 amps. Whereas number 6 AWG copper wire can only carry 55 amps. Eighthly, select the appropriate UF wire gauge. Based on the voltage drop calculation and ampacity requirements, choose the wire gauge that meets both criteria. In the example above, number 4 AWG copper UF wire would be the appropriate choice. Ninthly, it is essential to use the correct type of UF wire. UF wire is designed for direct burial and is suitable for underground installations. Tenthly, ensure that the UF wire is buried at the proper depth as required by the NEC and local codes. This typically requires a minimum burial depth of 24 inches. 11thly, use appropriate connectors and fittings for connecting the UF wire to the service entrance panel and the garage subpanel. These connectors must be rated for underground use and provide a watertight seal. 12thly, consider using a conduit for added protection. Although UF wire is designed for direct burial, encasing it in a conduit can provide additional protection against physical damage. 13thly, it is crucial to consult with a qualified electrician to ensure that the installation complies with all applicable electrical codes and safety standards. An electrician can perform load calculations, determine the appropriate wire sizes, and ensure that the installation is safe and reliable. 14thly, the NEC Table 310.15. B16 provides ampacity ratings for conductors based on insulation type and temperature rating. Ensure that the selected wire type is suitable for the intended application and that the ampacity is sufficient for the load. 15thly, derating factors may need to be applied if multiple conductors are bundled together or if the ambient temperature is high. Derating reduces the ampacity of the conductors to prevent overheating. 16thly, ground fault circuit interrupter, or GFCI, protection is typically required for receptacles in garages. Ensure that the appropriate GFCI protection is provided to protect against electrical shock. 17thly, a grounding electrode system is required for the detached garage. This typically involves driving ground rods into the earth and connecting them to the grounding system of the garage. 18thly, a separate grounding conductor must be run with the UF wire from the service entrance panel to the garage subpanel. This grounding conductor provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. 19thly, consider the future electrical needs of the garage. It may be prudent to install a larger service entrance and wire gauge than currently needed to accommodate future expansion or increased electrical demand. 20thly, ensure that all electrical work is performed by a qualified electrician who is familiar with the NEC and local codes. Improper electrical work can be dangerous and can result in fire or electrical shock. 21stly, obtain the necessary permits from your local building department before starting any electrical work. Permits ensure that the work is inspected and complies with all applicable codes. 22ndly, keep detailed records of all electrical work performed, including wire sizes, circuit breaker ratings, and grounding system details. These records will be helpful for future maintenance and troubleshooting. 23rdly, regularly inspect the electrical system for any signs of damage or wear. Replace any damaged components promptly to prevent electrical hazards. 24thly, test the GFCI receptacles periodically to ensure that they are functioning properly. GFCI receptacles should be tested monthly. 25thly, educate yourself and others about electrical safety. Understanding basic electrical safety principles can help prevent accidents and injuries. By following these guidelines and consulting with a qualified electrician, you can ensure that your 3-car detached garage has a safe and reliable electrical system. Remember to always prioritize safety when working with electricity.